Okay, well, thank you. The timing on the presentation is going to be longer than you might think. It's there's a lot to cover. And here's the takeaways. I'm hoping to do this to complete this in hour 45 minutes, 2 hours. But we'll get into it. And if people, I'll be looking for comments on chat as we go, and then every X number of slides, I might look at them and go through them, so we can do it that way. And then at the end, there'll be a Q&A session. Here are the 8 takeaways that we're going to try to do today. Um, how and what to think before you code, how thinking can be reused exactly like coding can. Well, you can see it on the screen. I don't have to read it. But these are the 8 bullet points that I want to cover. And the last one is how software architecture is increasingly tied into AI. And that's really the future of where things are going. Okay, so for software architect, uh, the 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 uh, it was listed as best job to hold in the United States by Money Magazine, and Indeed Employer listed it as the first in their list as well in 2020. Um, Question is, so we'll start by saying, in terms of how does a software architect think, let's start by looking at what a software architect is. So this is the Wikipedia definition for software architecture. Um, that is a software domain expert, someone who understands, and when I say software domain, what I mean is retail industry or the healthcare industry or travel or education. Each of those is a separate domain with a given set of applications, and the architect is trained in putting those applications together and architecting additional applications and making it fit in with what's already running within the enterprise. So to understand the process of architecture, I think start with understanding what architecture is to see what software architecture is. So let's assume we're architecting a house. So this might be the functional specification from the home buyer to indicate what they want in a house. In this case, um, it's 3 bedrooms, 2 bath, 2,000 square feet, 2 car garage, things about the master bedroom suite. They want a whirlpool bath, twin sinks, solar heating, internet capability, of course, security system. So that's what you hear from the customer, but from the home buyer. And you're an architect, and your job is to build that house. So where do you begin? How do you start by taking that and figuring out what the customer really wants? Well, this is the wrong way to start. You don't start building the house. You need to do more. They're basically, what we're going to talk about is the stuff that comes between listening to what the customer wants and actually starting building. And that's what software architecture is for applications. It's what architecture is for houses. So what does an architect do when starting the design of a new building? Okay, so you have the customer, planning documents, physical system decisions, who makes the things, and physical installation. So, for example, what that means is that the customer is the buyer. The planning documents are the architectural blueprints, the blueprints of the house. The physical decisions are made by a general contractor. So where the blueprints say going to be this wiring going here, and the general contractor figures out, well, it's going to be copper wiring, it's going to be this heavy, it's going to be. So those are physical decisions that you make, taking the actual vision for the architecture and bridging between what that customer wanted, what the blueprints say, actually getting it to a point that a skilled worker, plumber, electrician can come in and deal with it. So the first step in what the building architect does is to solidify the functional specification, to take what the customer said they wanted and to figure out how to get it to a form that you can actually build it. So this again is the functional specification. Um, this is the spec. What do you do now? Start. Wait a second. Oh, we're having some troubles. Start by asking questions. So your first question might be, shouldn't the house have a kitchen? What about closet storage, a laundry room? You're using your knowledge, if you're a building architect, of what buildings are and how they're constructed to ask the end user to get them, or the buyer, the purchaser, to get them to specify something that you can build and that will have a reasonable probability of being what they want. So some of the things that you might ask, what are the interactions between components? The size of the bedrooms and the location of rooms. How can you meet high level requirements? Um, Customers say they wanted security. Well, what are the details? There's a huge difference between providing security through locks and window bars and providing it through an electronic security system that videotapes people at the door. Customer has to think about it. They have to drill down deeper into what they want. And working with the customer to get that description is part of what an architect does. Identify the trade-offs. When you're building a house, um, there's good construction material and there's cost, and you need to weigh that. Um, how many features you want versus the move-in date. When do you want it and what should it do? All of that goes into the architecture of the eventual house that's being constructed. And what the architect incorporates all of that knowledge into a set of blueprints. So you have a customer gives the requirements to the architect constructs blueprints, and those blueprints go to the contractor, who then winds up explaining to the workers exactly what needs to be done. So, what does a software architect do when starting development of a new software application? Or in other words, let's see if there are parallels between what a building architect does and what a software architect does. We're having troubles on the. Okay, there we go. Um, so if you look at building a new software application, the customer is the domain expert. If you're building an enrollment system at a college, the customer is the registrar. If you're building a library system, the customer is the head librarian. If you're building a retail system, it's someone who understands what the application needs to do. A software architect, instead of blueprints, constructs what are called UML artifacts. And we'll see one or two of these during the lecture. These are the equivalent of blueprinting. Instead of a home, it's blueprinting an application, an end user application. The architect or the designer worries about the equivalent of the piping and the wiring. Um, what data store are we going to use? An Oracle data system or whatever? Is it going to be in the cloud or is it going to be in a data center? What language are we going to write it in? But those are things that don't have directly to do with the application itself. They're just the things that every application needs to rest on. And the parallel with the plumber and the electrician, that's the programmer, the one who creates the code that supports the application. So again, very much like building architect. A software architect job is to ask questions, identify all the components that you're going to need in that application by talking to the domain expert, defining the interactions between those components, defining how they hook to external components. So, in the sense with a house, you might say, well, you have building codes, you have to deal with an application. You have to say you have all of the other applications inside of the enterprise that this application is going to be deployed into. Um, Exploring high level requirements, trade offs, the blueprints for all of this that document the thinking of the software architect are UML diagrams. And that's that's the piece that captures the thinking of the domain expert in a way that can be brought forward so that the programmers can actually implement what the domain expert is thinking about. We're going to basically focus on step one of this process. You've got a functional specification, and we're going to use that to define what the abstractions are that reflect the requirements of the application. We're gonna look at how you hear what customer thinks is wanted and how you convert that to something that can eventually be implemented. So we're going to begin at this point. Let me just check for a second to see if there are. Okay, okay. So let us start down the untraveled road. This is the effectively the functional specification for an enrollment system at a local college. And I chose this because I know it's one system that everybody in listening to this has dealt with. You want to enroll to take a course. This is the description for De which is where I teach. Um, uh, Courses are offered by departments and available quarterly. Each course has an identifying number, and so on. You must produce a working solution. Where do you begin? Um, and so you've got a description. How do you start? Where do you begin to architect that solution? And this is wrong. This is as wrong as the starting to build a house based on the functional description. What we're going to talk about for the rest of this presentation um, is how what comes between that functional description and the code and when you start coding. So here are the software architect responsibilities. And the first responsibility, identify all the components. And that means asking questions. Take the functional specification and make it into something that can be built. It requires interaction with the domain expert, and it requires, so start by identifying the words in the functional specification, which must be refined to, to be the abstractions that the application is going to be based around. And so this is the enrollment system. College courses are offered by its departments. Each course is assigned a teacher who is qualified and willing. It's assigned a room. Students may attempt to enroll, and so on. That's the description of the application. We've circled or we've highlighted some of the basic uh, nouns that might form the basis of the abstractions in the application. So these are the first pass attempt to say, if you're doing an enrollment system at a college, these are the basic objects, the basic classes that are going to be defined. College course, teacher, department, room, and student. So now, and it is true that a software architect can come into work in the morning, stare at the ceiling, um, go out to lunch, come back in the afternoon, stare at the ceiling, go home, full day's work. And the real issue is trying to think of what could the architect, what does the architect think about in starting to architect an application? In this particular case, an enrollment application at a college. So here's the first thought. If you look back at the application description, uh, students may attempt to enroll in a course if they are paid up. You're thinking about that, and you're saying, "Well, wait a minute. Um, uh, can a room and a teacher be assigned to a course?" So you want to take a course. Let's say it's Java, advanced Java programming or something, and you want to enroll in the course. The course needs to have a room and a teacher. Can you assign a room and a teacher to a course? And the answer to that question is, well, it gets tricky. A course could be taught in several rooms. You might have Java, advanced Java being taught here at this time in this room with this instructor. And it might be taught here and it might be taught here. Um, Several rooms, several teachers. Can a student enroll in a course? Well, if you enroll in a course, which room are you enrolled in? Which teacher do you have if you're taking advanced Java at a college that has several teachers teaching it and it's offered in several rooms or virtually at different times? And the answer is no, you can't, which means you need a new abstraction. If a student has to enroll in something, a teacher has to teach something, but it's not a course. It's something different. It's a section. So once you see that, a lot of the architectural issues for that particular concern vanish. A section has a room, teacher, students, and it meets at certain hours. So if it's CS 101, introduction to Java programming, it's section 5 or it's section 6. And that's a section, when you have the section, that section has a room and a teacher and a bunch of students. Course has description, a name, number of credits, what textbook is used. The section is the instantiation of that course, and you can have many sections of a single course. And once you have the idea of a section, you've added a new abstraction to your solution. You've reworded the way people are going to think about it because the original description could not be implemented. When you add section, you're closer to something that can be. You're architecting a solution from an original functional description. So we continue to refine the abstraction. One of the requirements of the system is that a teacher has to be able to teach that section, which means it can't conflict with the teacher's schedule. And a room has to be able to hold that section, which means it can't conflict with the any other sections that are in that room. Likewise, a student needs to end that section, which means their schedule um, can't conflict with when this section is offered. So how do you avoid writing duplicate code? It's a requirement of the application that people's and rooms and teachers' schedules have to accept the schedule of the section for when it's taught, and which means you're going to have to write the code to do that schedule detection. You can write it once and insert it into um, teachers, rooms, and students, or you can create a new object which contains schedule conflict detection code, which means a student would say, well, does this section fit with my schedule? Likewise, a teacher would say that. Likewise, a room would say that. And all of them would be using the same code that's in a separate object that determines whether there's a schedule conflict. So you have each of them contain their own schedule object. Student has a schedule, teacher, room. They all access schedule to find out if there's conflicts. So what we started with was an enrollment system with 6 objects. We're now adding 2 more, schedule and section. We're staring at the ceiling and we're saying, when you think about the problem, you start looking at the missing pieces. You're architecting a solution instead of saying, don't you really need a kitchen in this house? You're looking at the functional specification and trying to imagine implementing it and asking questions that reveal hidden abstractions, hidden objects that are going to be part of what the programmers are going to be implementing. One more. We're having a little trouble in the transitions. Okay. Another abstraction. What's a prerequisite? Well, a prerequisite for a course, because one of the requirements is that a student will not take a section, not enroll in a section, or take a course that has prereqs that the student doesn't have. So the question is, what is a prereq? Is it a course, a section, a string containing like Java 101? Or is it the Java 101 course? Or is it a different object entirely? Well, you could say a prereq is a course. Prereq has a department and a course ID. A course can have multiple prerequisites. Um, a prereq can have multiple prerequisites. Well, maybe if a prereq is a course. Prereq is a section that doesn't make any sense. No one's going to say, you must have taken that section of that course in order to take this one. You must say, you may have taken that course. Could a prereq be a simple name of a course, Java 101? Or is it a new type of object entirely? So you're staring at the ceiling and you're thinking about that. One of the things you're going to have to deal with in the application based on the functional description. One of the ways that you might resolve this, if you're a software architect coming in to architect an application that's going to allow enrollment at a college, look at a catalog. And when you look at the catalog, you find out some interesting things. Prereqs have types. There are a prereq can be advisory or mandatory. In other words, you have to have taken this course, or it would be good if you took the course. Prereq may not involve a course at all. A prereq for a course may be prior experience with the Java programming language. So pointing to a given course doesn't really work. And so what you're coming to the conclusion is you might say, well, the attribute list for a prereq has an enumerated variable that can have two uh, possible values, advisory and mandatory. It might have a string that, if it exists, like a text requirement, optionally. It might have a course ID, uh, Java 101, for example. You're still going to have to figure out how to represent the Boolean logic that says the prereq for this course is that course or that course, or it's that course and that course. So you're looking at a bunch of attributes and you're looking at some Boolean logic that allows them to combine with each other. And you're realizing it's an object. And this is the sort of stuff that a software architect thinks about when they're architecting an application. You're not producing anything yet. You're just trying to figure out what are going to be the classes, programming classes, or the objects when they're instantiated. What are the objects that are going to be manipulated in the student enrollment application? So the first step, read and understand and clarify the functional spec, and then identify those application abstractions that comprise of functional specifications. And so this is where we are now. We've added 3 in the space of about 10 minutes. This would be the morning staring at the ceiling. Schedule, section, prereq. Now we've got 9. How many more are there? Well, there's more. Um, uh, as we'll see. Obviously, we're missing student, but we're going to add that later. The next step is taking the abstractions and creating an application vocabulary. The goal here is to have everybody on the project, and that means the end user and the domain expert and the programmers speaking the same language so that when you say course, everybody knows what that means. When you say section, everybody knows what that means. All right. And it's that application vocabulary that the architect is primarily tasked with maintaining. You can think about it as there's a domain expert, and the software architect is a translator between the domain expert and the programmers. So when the domain expert says something like um, a student enrolls in a section, doesn't say course, says a student enrolls in a section, you can have programmers implementing section and student. And if a new requirement is added, if the domain expert says, and foreign students will be charged more money than right, the programmers go, foreign student, okay, that's a type of a student. Maybe it inherits from student. Um, and now we're going to change the how much does it cost routine to reflect the new requirement. If everybody's speaking the same language, if everybody uses the same definition for the abstractions that comprise the application, then the functional spec requirements can be directly read by the programmers, which is what you're trying to do. That's one of the main goals of a software architect, to define the vocabulary of the application so that everybody is it's saying the same thing. And nobody's saying a student enrolls in a course, which is impossible. They may have started by saying that, but after the architect determined that there's a section and students enroll in sections, now everybody is saying that. You're manipulating the same set of abstractions in the same way. Determining the relationship between the abstractions, and we'll look at some relationships. Um, there is a concept that if you're a programmer, you should really understand, and it's design patterns. I'm not There's not enough time to get into that, but design patterns allow the reuse of thinking in the same way that software libraries allow the reuse of code. You can reuse thinking. And we're going to look at an example of that. This is an example in this application where we encounter a design issue and we apply a design pattern. So let's take a look at that. This is a UML artifact. It is a conceptual class diagram of an enrollment system. Well, in this particular case, of how to produce the schedule of classes. So you have a college, and the college, one college has n departments. One department employs n teachers, owns n rooms, and offers n courses. A course contains prereqs. Um, the teacher instructs sections, rooms locates sections. A course instantiates n sections, and teachers' rooms and sections have schedules. This diagram is conceptual. It is what, if you show this diagram to the domain expert, the domain expert looks at that and says, could be able to look at that and say, yes, I get that. This is the essence of what an enrollment system, of a system that uses to produce schedules of classes, right? Because when you produce the course, the catalog or the schedule of classes, um, you have listed all of the courses and all their sections. Each section has a room and a teacher. They're offered by department, they're organized, and the college has many departments. This is the essence. If you were a programmer hired to work on producing a schedule of classes system, this would be an extremely helpful diagram. It would document the basic abstractions of the application, and it would show how they're interrelated conceptually. So looking at this, we're going to focus, oops, we're going to focus on the one to n aspects of the relationships. There's one to n aspects here. There's n to one aspects. One college has n departments, one departments have one college. There's one to one relationships. Um, uh, a room has a schedule, right? One room has one schedule. So we'll look at those relationships because they're very instructive. So this is one to one. Every teacher has a schedule. So you looked at teacher and schedule. If you were implementing it in C++, it would be class teacher has a private schedule object that it uses to keep track of whether the teacher can add a section to teach. A one to n relationship, one teacher teaches n sections, and which means that a teacher has to have some kind of a collection of sections, might be an array of section pointers or section references. A section only has one teacher, but a teacher has n sections, means a teacher has to collect sections. N to one is n things connect to one thing. So n sections have the same teacher, and teachers have the same department. So if we're looking at the teacher object, again, in addition to a collection of sections, a teacher object has a pointer to a department. So if you change something about the department, like the dean, every teacher would immediately, by pointing to department, would see that the department's dean has changed. And so changing the department's dean in one place would change the dean of every teacher in that department, end-to-one relationship. So we're pretty clear on one-to-one and one-to-n, how it's represented, and n-to-one, how n-to-one is represented. There's one other possibility in terms of a relationship, and that's n-to-n. What's an example of an end-to-end relationship? Um, a student may be enrolled in many sections, and every section will have many students enrolled. So it's end-to-end. Question is, how is that represented? Hang on, let me just look at the questions. Okay. How are you handling? All right, so let me just look quick. How are you handling requirements, traceability, inherence, and evaluation of the goodness? Um, we'll, we'll come to that. And that's a great question to ask after the presentation's over, because we'll see examples of how that happens. We're not going to be able to get into inheritance because we don't have time, but we can address that if people are interested after the presentation's over. Question. Thank you. Um, so the question here is, okay, how do we handle an end-to-end relationship? Student has n sections, section has n students. Okay, let's try two separate pointer arrays. One student has n pointers, one student has an array of n sections. One section is taken by n students. So we've got the one to n going this way and the one to n going that way. And we have an array of student references in a section. We have an array of section references in a student. Solved, right? Not really. This end-to-end relationship has data. So a student taking a section gets a final grade. Maybe there's attendance records, exam grades, teachers' comments. All of that is located with one student in one section. The question is, where is that data stored? Right? Because if you store it with the student, you don't want to store it in both places. But if you store it in one place, then if you wanted to say give me the grade. Suppose you stored it in student, and then you said, give me the grades of all the students in my section. Well, all the section would have is the student pointers. So they'd have to go into the student and then say, go through and find out for this section what grade you got. You'd have to do that for every student. If you stored this information in the section, then the student, if trying to find out what their GPA was, would have to go to the section and say, okay, I'd like you to look at all of your students that you're pointing to and find out what grade you assign that student, because I don't have that grade. Um, or you could store it in both places, which is bad because you don't want to have duplicate data. So if the grade is changed, you got to change it in two places. Where is the information stored? Um, if you have an end-to-end relationship with associated data with the specific one-to-one, there's data associated with it. Having an end-to-end relationship is a design error. And at this point, if you're an architect, you go, my God, how am I going to deal with this? And the thought occurs to you, you could not possibly be the first software architect deal with an end-to-end relationship that has data associated with it. Couldn't be the first, right? And you start thinking there must be a design pattern which documented the thinking of a software architect in the same way that a software library documents the code of a programmer who dealt with the problem you're trying to deal with before. So the software design pattern in this case is called the Junction class. And it says, put something in the middle. So a student, let's put a thing in the middle. A student has an array of thing references. A section has an array of thing references. The thing points to the student, points to the section, and contains the data. So if a student wants to find out their grades, they go through their collection of things and say, what grade did I get? If a section wants to find out all of the grades it assigned, it goes through its list of things and says, what grade did that student get? The student goes through and says, what grade did I get in that section? And the thing is an object that sits in the middle and links the two sides so that the data only appears once, but it's directly accessible by both the student and the section. It's a design pattern. It solves, in this particular case, design issues that the software architect is worried about. What do we call the thing? Transcript? No, because a transcript's a collection of stuff that a student has. A roster? No, that's a collection of stuff that a section has. More than one student's involved. Registration. A student has multiple registrations, maybe enrollment, a student place, their names. And you might say, what should we say a thing is? A student has multiple things, one in each section. A section is initially created with n things that students will be assigned to. Each thing that a section has is either occupied or empty. And a thing has all of the information for one student in that section. You might call it an enrollment or a place, but the best answer to it is a seat. And once you're staring at the ceiling and you say, we'll call it a seat, the vocabulary of the application becomes immediately enriched in a way that's important for its solution. So now you can say things like a student has multiple seats, one in each section. A section is initially allocated with n seats. It can take 40 students. Each seat is either occupied or empty, or waitlisted. If the student has been assigned to the seat, but it's a waitlisted seat, they may or may not get into the section. Seat is a concept immediately known to the domain expert, and now you've created an object that you can give to a programmer and say, I want you to implement this seat. And a seat is an interesting object to implement because Among other things, it has behavior. When you say, I'd like to enroll in this section, the section can say it has the enrollment method, but what the enrollment method does is very different based upon what happened before. Is every seat occupied? All right, then we're going to waitlist a new student. Is every waitlisted seat full? Well, we're going to reject the enrollment. Different behavior for different states of the seat object. Bottom line is, seat isn't just a collection of data, it's an object with that data and associated behavior. It's a concept known to the domain expert, and it's a concept that a programmer can implement. It's an object, and it's added to my application. So this is kind of how the seat fits into the conceptual class diagram. So now we've got this as the enrollment, the set of enrollment applications. We've also got, we've neglected, there it is, there's student, college, department, teacher, student, course, room, schedule, section, prereq, and seat. These are going to be at least the first pass at the basic abstractions that we're going to use in the enrollment application. How could you begin to implement an enrollment application if you didn't first architect the set of objects types that you're going to need to manipulate in creating that enrollment application? So this is the functional specification after we've done our magic to it. Okay. Indiana College, Indiana College courses are offered by departments, a number of credits, an optional set of required prereqs. Each course is instantiated by one or more sections. Each section is assigned a section number and a schedule. A section is assigned to a teacher who is qualified to teach that course, has no schedule conflicts. Uh, Section is assigned a room, which must be free during those times. Students may then attempt to enroll if they are paid up, and so on and so on. And if they're not enrolled in another section with a conflicting schedule, depending on the size, waitlisted, the section may be denied. If accepted, she will be assigned a seat. Her attendance will be tracked, and so on. This is the functional specification for the enrollment system after people are thinking about it. This is a functional specification that can be given to developers to implement. There's a lot more that you want to give developers, but this is a basic functional specification of the system. It has all the major abstractions and how they're used. It's interesting that prompt engineering is the process of structuring text that can be interpreted and understood by a generative AI model. A prompt is a natural language text that describes the task that an AI should perform. That is the Wikipedia definition of prompt engineering. And that is exactly what we just did. So, in a sense, software architecture can be viewed as prompt engineering. It is it is the taking of a domain expert's thinking and creating at least at the beginning, creating a functional specification that allows programmers slash generative AI to create an application. And the AI is basically replacing a lot of the steps that happened after something like this is created. Now, there's other blueprints that are going to be refining that solution. And we're nowhere near yet saying this will generate an enrollment application. There are an awful lot of issues that have to be dealt with. This is a start, and this is a good first pass at what prompt engineering might do to describe to generative AI, this is the kind of system I'm building. Because the original functional specification couldn't do that. It had to be analyzed and designed. So yeah, software architecture in the first phase of it is very similar to what people are starting to realize is prompt engineering. So you could say that there's been somewhat of an evolution here. The domain expert, we basically, the software architect, who is now kind of a prompt engineer as well, is taking the domain expert's original vision of the functional specification and creating a revised functional specification, which is being passed to a programmer and copilot. I mean, if you look at the future, that's going to be something of what's going on in the future. The prompt engineer is the translator between the domain expert and the programmer and copilot. And it's not only the revised functional specification. We looked at that conceptual class diagram. That's also something that gets passed to the programmer and the copilot. And again, it comes from, there's functional spec here. There's there's revised functional spec. There's conceptual class diagram, and there's going to be other attributes. Well, there's going to be an attribute list and other UML artifacts that are going to be passed to the programmer and the copilot, all of which will make sense to the domain expert, all of which will serve to guide the programmer and the use of copilot in generating the actual application code. So let's view an example of a use case. And the use case is in this particular environment. So let me rephrase. One of the things that you get after the functional specification, you get a detailed set of use cases. What are the things that the application has to be able to do? And you look at, there is a formal definition of a use case. And the use case is an English language definition of specific things that the application has to do using the abstractions that we've just identified from the functional specification. And we've done more with those applications, steps that I'm not going into here. If you're architecting a solution, you've taken that application, you've got the abstractions that formulate it, and you've looked at the attributes, the detailed attributes of those abstractions. You've looked at the behavior of those abstractions. You've refined them into classes. And now what you need to do is show how the classes that you've created for the application will do all of the use cases that the application has to do. So here's an example of the enrollment application. You have to create a new section. You have to assign a teacher, add a room, enroll a student in that section. Let's see, process the end of enrollment period. So you may be dropping sections that didn't get enough students. Processing end of term, assigning grades. There's dropping sections and reassigning teachers. There's maybe, in terms of use cases for an enrollment application, there's maybe 20 to 30 use cases, things that it has to do, things that a user can ask it to do. We're going to look at one of those. How do you enroll a student in a section? So here, no, we're going to do it. Let's see. Okay, how do you enroll a student in a section? So you think of some restrictions. A section must have open seats. Before you can enroll a student in a section, what do you need to do? A section must have open seats. The student must have paid tuition. The section schedule must not conflict with the schedule of any other sections that the student's enrolled in. The student must have completed all the prereqs. Those are requirements of the system before you can let the student enroll in that section. On success, you've created a seat which connects the student and the section, and the section schedule is added to the student's schedule, and the students enrolled has been assigned a seat, and their schedule reflects that. That's kind of what needs to happen before a student can be enrolled in a section. There is a UML artifact that documents that in a very formalistic way. It's the sequence flow diagram. A sequence flow diagram, what it does is it documents the orchestration. Or in other words, uh, um, um, if you think of a use case as um, a Beethoven symphony, right? Then the sequence flow documents what every instrument in the orchestra has to do in order to play that song. So the sequence flow is an orchestration of a symphony, and the each object type is like the tuba and the God help us the accordion, and um, and the piccolo and the whatever instruments are in that band. Um, it shows how each one comes in and does what needs to be done to make that song happen. And the sequence flow documents what each object type that you've defined, which abstraction that you've defined, what that has to do to support this particular use case. The end result is the required public methods have been identified for each of the abstractions in order to produce that use case, in order to serve that use case. So let's look at one of those and just talk our way through it for a minute. So this is the sequence flow of student X enrolls in section Y. And it starts out what your application would get sitting going across the line is here, I want to do an enrollment. Here's the student ID. Here's the section ID, right? And so you start by converting, and the vertical lines in this diagram are the different abstractions and how they're used. And any line coming in to an abstraction in this diagram is a public method. And any line going out is a collaboration. So the first thing that happens, the client, which is the main line of the application, gets the request, enroll, double quotes, 12345, that's the student ID. Uh, CS 101-5 is the section identification. It has to first convert the 12345 to a student object, and then it has to convert the section string to its section object. And so it calls on the college to do that. At that point, it now has a pointer to the client, the main line has a pointer to the student and a pointer to the section. And it asks the section, enroll that student. It could have asked the student to enroll itself in that section. If the architect had chosen that for the call, everything here would be flipped in reverse. That is, the student would now be enrolling in the section rather than having the section enroll the student. But we chose to do it this way. And by the way, this diagram, there are four possibilities, right? You can ask the student to enroll in the section. You can ask the section to enroll the student. Both of those are fine. The third option is you can ask both of them, so both programmers implement it, and that's not good. The fourth is you didn't ask either of them, in which case it's not there. So the sequence flow shows how the sequence of operations will flow from one object to the other in terms of performing or meeting the requirements of this use case. And it shows what every object has to do. So section must have open seats. Okay, but section has a public method called is there room? And that will determine it. No schedule conflicts. So you're asked, the student is asked, can you take the section? And this vertical square here is, can you take the section? And there's the return. This is the stuff that happens to determine whether the student can take the section. And it shows, okay, the student calls itself, is it paid up? Fair enough. Now you have to determine if there's a schedule conflict. Okay. So you ask the section, give me your schedule. Then you ask your schedule, is there a conflict? And that determines it. This will be able to determine if there's a schedule conflict. Then you ask the section, give me your course, and you ask the course, give me your prereqs, and then you verify that all of the prereqs are met by that student. If all of that's true, if there was no schedule conflict and there was no course conflict, you return yes or no. And the thing about the sequence flow is it only shows success. It isn't a flow chart saying you failed. If at any point you fail, it stops. This is just documenting how everything works if everything succeeded. And what you're coming away with is, okay, let's look at the lines coming into section. The public method on a section is enroll a student, is there room, get your schedule, get your course. Yeah, those are public methods of a section. They're in order for a section to compute this, to work in adding a student. These are the public methods. When you go through, and this is the thing that we don't have enough time for, but conceptually, I want you to understand this. When you go through all of the use cases and you produce sequence flows for all of the use cases, what you get is all of the public methods of every object to support all the use cases of the application. You basically debug the design. And we'll talk about that a little bit more. But this diagram, if everything succeeded, then you 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 create a new seat, giving it the section and student. You add the seat to the student, and then you've added it to the section, and you're done. So that's the sequence flow matching the sequence flow use case. This was the diagram that matches the use case of a sequence. A lot to kind of get your mind around. But conceptually, I wanted to introduce that because it's really, really critical. If you what we now have, so for example, you now have the functional spec, the software architect translate that into into the revised functional specification. We now have the use cases, all of which the domain expert knows, because the domain expert can deal with the use case. The domain expert can totally define the use case. And what you're taking that use case as a software architect and creating the sequence flow diagram, which is a thing that the programmers can understand. As a software architect, you're the translator for that. And, we had the co-pilot and the pilot. 5 years from now, maybe co-pilot alone. Don't know. And it wasn't easy to find a picture of a robot piloting a plane, by the way, but I used AI for that. Okay. Um, three questions that let me just look for any questions here. Oh, okay. Um, okay, well, thank you. All right. There's a couple of more questions I want to answer before we're finished. The first is, how do you implement this stuff? I mean, you're the software architect, and there is an old saying that a software architect who never coded, who doesn't know how to code, is, I'm being recorded, so I have to be careful here. It's like a priest at a wedding, in a way, right? He enjoys the ceremony, but can only imagine what comes after. And by that, I mean, if you're an architect and you're going to be architecting this, you really do need to understand how to code, because that's what comes after. Um, and knowing how to code is understanding better software architecture and understanding what design patterns to use and advising the programmer. And if you don't know how to program, the programmers will not have respect for you. So you really do need that. Um, in order to implement object-oriented design, which is what you're doing, an object-oriented language is needed. Um, and the question is, where did that come from? Um, I wanted to do in 20 minutes an, an overview of the things that underlie software language development over the last 50 years. I wanted to do that in 20 minutes because it's instructive to understand how what the architect is envisioning can be made into code, and how programming languages have been evolving to allow that to happen. If you go back 50 years or more, you go back to 1970, so 5 years maybe. This is 55 years now. Now, you may have heard of Bill Gates. He made a good living out of this. Um, this is what BASIC looked like. It had line numbers, which is what, and REM meant it was a remark. And so you'd say the variable A7, you're going to compute sales tax. So you're going to take total earnings. A9 is the, A7 is the total earnings of your company. A8 is the percentage of sales tax. And A9 is a variable that will be clobbered with the actual sales tax amount. It's an actual code back then. Go sub 6,000. And 6,000 says, I'm the compute sales tax. A7 has the total, A8 has the sales tax, A9 equals A8 times A7, return. And that would return you to here. And you would print out A9. This is so primitive that you might as well be using machine language, but it's the beginning of how you split off a piece of code from the main line. It's the best you could do. You had a subroutine which had a return statement. The subroutine had no name, and it had no variables of itself. It used the variables that everybody had. So A9 was the same variable for the main line as it was for the subroutine, which meant that only one person could write the code. Because how could you basically break up your application? Think about what it would mean to try to write an application that had 5 subroutines in it. You'd have to know what each variable used by each subroutine was and make sure they didn't conflict. And if you wanted to get a subroutine from somebody else, they'd have to tell you what variables they use, and you'd have to map it up against the variables that you were using and the subroutines were using, because every variable was global. And that was the beginning. So basic, the variables were program wide, they were global, and there were a fixed set of variables. Then Fortran came along, and Fortran was a huge conceptual jump. It had subroutines. So the subroutines were, you could have subroutines with respect to You can have variables, excuse me, with respect to a subroutine. So that if you're writing the main line, you could say, I'm going to call the subroutine to compute sales tax, and I don't have to worry what variables you're going to be using, which means you can go off and write it without knowing what application it's going to be used in. You could do that with Fortran and with later variations of BASIC, but you could do that with Fortran. And that was huge. It meant you could take a project and break it off into subcomponents and have those subcomponents written and integrated in. They wouldn't be breaking everything because they were using the same variables. They had their own variables, they had their own scope. And the scope of the variables, you had global variables, but the scope of the variables were local to the subroutine. It was a beginning, but it wasn't enough because the fixed set of subroutine, of variable types, wasn't enough. In other words, if I was trying to put together the enrollment system, I'm an architect and I'm trying to use Fortran. Yeah. I have subroutines. But what is a student? Well, I don't know. The language doesn't let you define a student. It lets you define integers, floats, strings, right? How do you define a student? You have to how do you define an array of students when you can have an array of integers, an array of strings, and so on? How do you define an array of students? Where is the mapping of the vision to the language? It's not there. And then C came along, and C was marvelous. It was a low-level language in the sense you could have register variables. It had memory management, which, and I don't know if people here know or ever programmed in C, but it used a thing called malloc, memory allocation. And the first time I heard that, I mean, I said, how do I allocate more memory? And they said, you can allocate more memory using malloc. And I thought that was like an ancient Semitic god. Oh, malloc, please grant me more memory. And you got it, right? But anyway, that was one thing it had, which none of the other languages had. But it also had a struct. And a struct was the first time that a language construct would map what the architect was thinking about. That is, what is a student? Well, you define the structure of a student. A student has an integer student ID, and it has a string name, and it has a float GPA, and all of those things are a student. And you could have a pointer to the student. You could have an array of students. You could have an array of pointers to the student. It was the first time that the architectural vision for what an abstraction was actually reflected in the code that you could see. So the programmer, for the first time, had an idea of what a student was before they couldn't construct it. Now they had an idea, right? But there were problems because the all of the logic was in one place and all of the data was visible to all of the logic. So you could say, we got local variables that are in routines, but those routines would be sharing. So if you said now we've taken the data, the variables, and we've put them into these structures, but now we have multiple subroutines that share those variables. So I write a subroutine. My variables aren't local, they're global because the subroutine to compute grade point average or the subroutine to set a student's phone number or the subroutine to enroll a student in a section, that subroutine is going to be looking at stuff. The subroutine to, I mean, all of the subroutines to do the things you need to do the use cases, they're all now using global data, which is defined by the student. So the data left the subroutine and it's back in the student construct, which all of the use case subroutines are using. And if one of them is broken, it affects all of them. If there's a change to the structured data, it affects all of them. And out of that, people realized they needed to have objects. And objects were the encapsulation of the data, the struct data, and all of the routines that used it were all hidden. What you got was the public methods of the 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 public methods that had the logic to use the hidden data. You basically had the public methods surrounding the implementation and the private data. And that was C++, plus plus, a language that was called C++ plus plus because it was post incremented C. Every C program was a C++ plus plus program originally. So they couldn't call it plus plus C, that'd be pre incremented C. They couldn't call it D, they call it post incremented C. Um, I'm not going to go through the other languages and what Java brought to the table. Basically, well, it made the language be the platform. Uh, write it once, run it everywhere was the vision of Java. And I was a Sun employee for 20 years, and I totally believe that vision. Um, Python made things simpler. Where we're heading now is another language, which is English. And the unit of English, we went from the function and the struct to the object to the functional spec and the use cases. The code, um, the oops, sorry, code um, is determined by more and more by AI. And if you roll it forward a decade, it's going to be that even for applications that run inside of an enterprise, and we're going to see why that's difficult to pull off. Um, Even if it does, um, how most of it can be generated with AI. The ultimate goal is to get all of it generated with AI, to have the software architect become the prompt engineer and to generate the blueprints. It would be as if an architect could take the blueprints, the detailed blueprints for a house, and specifying, yeah, we're going to use copper wiring and the bandwidth is going to be this much, the details, and have the house built by robots. Now that's a way off, but with code, that's a lot closer. Okay, let me just see. We've got okay, yeah, we'll talk about that at the end. Parts of it is coming to be reality, and parts of it I'm sure I'm not totally up on. Oh, thoughts on JavaScript and okay, I will answer that in a slide ahead. We're talking about languages that are used to actually implement like the back office, the thing that makes the world work, as opposed to more the front end. But we'll come to that. Okay, let's see. Three questions that are answered. How do you package this stuff? How do you deliver an application like the enrollment system that you've architected across the internet? This is a very quick diagram of a three-phase architecture. You have a user level, whether browser or tablet or smartphone, whatever. They're talking to a web server, which could be in the cloud, or it could be in a data center. I'm not going to get into servlets and how, but what you do have, and the thing to understand, your application, so the enrollment system application, is actually running on what is called an application server, and that could be hosting a lot of applications, hosting multiple instances of an application, but it's a separate server concept. It's running an application server. So we're going to pretend that the application, which is a client and a bunch of object APIs, and then the actual code and itself, that application is is running in a separate machine. And again, that machine could be in the cloud, it could be in the data center, it could be part of a machine. But the way the world works, a user logs on and basically uh, gets their user ID and password, and they establish a connection with the web server. The student then brings up an application like enroll, and they sit and they go, okay, they can't respecify, they can't enroll someone else in the course or in the section, but they can specify, hey, I want to enroll in this section. And what comes across and the network protocols between the user and the web service tier are things like JavaScript, Ruby on Rails, and so on. And that gets you from here inside of the web server. Um, there's maybe a servlet is basically saying, okay, this is the enrollment application, and it puts a request into this request queue and picking out of that request queue and dispatching to application servers is another servlet. And again, what you're really doing is intermediary between all of the users and, in fact, the application servers which are servicing those requests. So what comes across the line on top of the internal protocols here are REST and JSON, and most of the time. And basically what they convey is double quote enroll, here's a student ID, here's a section ID. That comes in, that those three strings come across the wire into the application server. And all of this is one application. The client is the main line of the application. It could be reading it from standard in, or it could be reading it through REST and JSON. But it gets these three strings, and it has to make those three strings work. It has to enroll that student in that application. And we've already seen what happens normally when you call a subroutine. You call it and it comes back. In this particular case, when the client calls student enroll in that section, that is going to cause a whole bunch, like a pinball machine. It's going one application is going one object is going to call another, call another, call another, bing, 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 and then it comes back to the client. That those internal calls in order to service enroll student are defined in the sequence flow that we just looked at. So that's kind of the way these applications are packaged. Now, how do you integrate this? How does the application connect to the other applications in an enterprise environment? There's an important distinction that needs to be understood. All right, hang on one second. Let me just take a look at some people are posting things. Okay. Okay, I'm going to get to the questions. We've got a couple of more slides to get through, and then we'll come to the questions. There are some good questions here. Okay. Someone said, what about Objective-C as a language? One language I do want to talk about for about a minute or two, and that's C sharp. C sharp is a language that was created basically, and this is opinionated, but and I worked for Sun for 20 years, so it's kind of backed up with something. Java, the beauty, what Java added to the language evolution was the language as a platform. Write it once, run it everywhere. And the thing about that is you could write it once and debug it everywhere. That was the beginning. But it got to be write it once, run it everywhere. And there was one company that hated it, and that was Microsoft. And the reason they hated it was because until Java, Microsoft, the operating system was the platform. You wrote to Microsoft's APIs. If you were a developer, you wrote it to their APIs, which meant like Hotel California, you could check your application in anytime you wanted, but it could never leave. It's kind of the Roach Motel of operating systems. The Java took the concept and said, just write it to Java and it'll run on a browser, it'll run on Unix, Linux, Windows, right? It disintermediated the developer from Microsoft. And what they did was they invented a language that was the equivalent of Java, but it only ran on Windows. How great was that, right? That's what C Sharp added to the mix. Um, okay, let's get back to we'll talk about Objective C. We'll talk about Objective C. Okay. There are two kinds of applications if you think about it. You can divide it up. Applications that work a lot standalone and applications that work inside of an enterprise. And I'm giving this talk in the Valley. And if you live in the Valley, you're very familiar with the standalone. You log into Amazon, you log into, you know, any application that runs Facebook, you log into the Google, what you log into something that runs alone. Those applications are different because they don't need their whole vision for how they develop their applications is different. They use agile programming. They say, look, don't worry so much about the architecture. Get it out there. People will use it. They will give you feedback. The main goal that you have in doing this is capturing eyeballs. So you race to get something completed and tested and send it out there. And if it doesn't work, you'll hear about it. And if you want a feature, you'll hear about it. And that's the vision of applications that run standalone and that run an interface directly to the user. And then there's what I call the non-Valley applications, which run in an enterprise. So the enrollment system that runs in a college. And if your company is making enrollment systems, then you have to understand enough about the college environment, understand how to get data because you're going to need student data that you don't take in. How do you get that data? What data do other applications need from you? Also, you don't want to ship it to colleges and get eyeball contact and then have them report back the errors. Because if the enrollment system fails, nobody can register at a college. And if you get a reputation for not fitting seamlessly and correct into that college, you're not going to sell any applications anywhere. It's the flip of how you develop applications. And you can hear people justifiably saying, don't worry about the architecture and the decisions. Don't delay the implementation. Get it out there. And those people are dealing with standalone applications. There are applications that I talk in the class that I give at the end of about applications like pilot assignment. And, for an airline, it's a very tough thing if there's a snowstorm and where do you get the pilot that's qualified to fly the plane anyway, point being, people write that application and they install it in different airlines. And if that application breaks, no planes take off. If the enrollment system breaks, no no students can register, which means you better do more upfront thinking on all of the applications of the back office, of all of the applications that make a retail enterprise work, that make a hospital work, that make a college work, that make an insurance company work, that make a bank work. All of those applications are part of the enterprise and they have to fit seamlessly and they have to work. And you don't go for eyeball capture. And the way that you develop those programs may not be agile programming. They may be thinking about it first and thinking of all the ways that it fits in to the enterprise environments that your application is going to have to run in. And a lot of what I'm saying about software architecture is targeted toward those sorts of applications where you look at the front end and you pick what you're going to do and you look at the products and you look at all of this and then a magical moment happens. You say, buy it. And at that point, the application servers come up because you're going to got to deal with the inventory and the warehouse and all of the stuff that you don't see, all of the visioning that has to go on to make that user request work, which has to seamlessly integrate together and have to be well architected and may be developed using maybe not non-agile programming or maybe agile programming with a lot more upfront thought. But that's kind of what we're talking about here. So how do you connect to the other applications in an enterprise? Well, let's see. Here's the student enrollment system. Here's the data that it needs from all of the other applications running in a typical uh, enterprise environment at a college. The catalog system, which gives you the courses and so on. Facilities management system is where you get your room data, like how big is the room and how many seats in the room and what equipment is in the room. Um, Schedule of classes gives you the section information, student information from the student information system, teachers coming from employment. All of this, you're getting data and creating your internal objects that you need to manipulate. What are you providing? What does the enrollment system provide? Well, imagine there's an emergency contact system. Emergency contact system basically says there's a fire, there's an armed shooter in the building. Who is in that room, right? Who is in the room? You ask the student enrollment system. The student enrollment system knows. It says, okay, what are the sections in that room? Okay, what's the schedule of that room? Looks at the will give you that. Will give the emergency contact system that. Looks then at the schedule and says, okay, which section? Looks at the section and says who's enrolled and the teacher. You want to save the teacher too, right? In addition to the students, and then notifies them. So you have to be able to not only get the data, but you have to be able to give out the schedule information and who's currently where to another system that might use it. How do you do that? Given the fact that different colleges may be using different vendors to supply these systems, how do you get the information you need from all of the systems in an enterprise? That's a big deal for a software architect. Okay. And it's answered this way. Usually, and particularly for educational systems, and I was CTO of an educational standards organization for a number of years. You define the data model of what a college is. And if that's defined, if the college is conformant, as all the high schools are, with that data model, then your application will plug in because it'll go to the data model to get that data. So everybody is putting their data in and taking data out of an enterprise data model, which has schema definitions for these things, using SQL probably to do it. And here are the different applications and what they put into the college database. So a couple of things. Because we're close to the end. Let me just see. Yeah, we're close to the end. Maybe about 5 more minutes. If you stayed with me this long, thank you. We're getting to the wrap up here. Um, how do you get to be a software architect? There's one piece that we haven't talked about yet. If you start with object-oriented programming skills, you're a software developer. If you add in object-oriented design and knowledge of design patterns, you're a software designer. Design patterns, even if you're a programmer, even if you're a software developer, you should know design patterns anyway. An example of a design pattern is inheritance. Now, my students come into my course knowing what inheritance is. They know how to do inheritance in a bunch of different languages. What it is, what it means, how to do it. What I add in my course is when to do it. That is, inheritance is a design pattern for reusing code, and expanding and hiding extensions. Anyway, point being, it's a design pattern, and there are a lot of design patterns that are very valuable. In a way, you don't have to know the details of them. You just have to know they exist. And then if you need it, you go, wait a minute, how do I do this? And you look and there it is. It tells you. Um, if you add in object-oriented analysis skills and domain knowledge, and that's the missing piece, domain knowledge. There are different software architects. It's not a one thing. There are retail software architects. There are healthcare software architects, education, travel. The reason is because you have to understand what else is out there. If I'm building an enrollment system, I have to understand a data model, and I have to understand the kinds of applications that are going to be running in the enterprise that my application is going to be running in. And that's different for different data models. I'm sorry, for different data domains. It's different in the same way that you wouldn't ask a skyscraper architect, an architect who understands, and I'm telling you, this amazes me. And there is an old saying, which I totally believe: sufficiently advanced technology is indistinguishable from magic. Okay, I'm on the 33rd floor of a skyscraper, and I go to the restroom and I turn on the hot water and it comes out hot. I have no idea how that works. Do they have 33 floors of hot water? And anyway, point is, would you take someone who can design and architect a 100-story skyscraper and say, okay, build a bridge? No, you wouldn't. It's a different kind of architect. It's a bridge architect. Would you ask a retail architect? Would you ask a healthcare architect or an education architect to design, architect a retail application? And the answer is no, you probably wouldn't, because here is a diagram, and it comes from the standards group that created the retail data model. And by the way, this is uh, an education architect being asked to design a retail application. Um, this is a diagram that retail architects live and breathe. The bad news is it's fairly complex. The good news is there's only one of them. If you understand what you're looking at here, you understand retail architecture, or at least you have a lead into retail architecture. I mean, just as an example, um, let me just find. Oh, here we go. You look for the concentrations. Whenever you look at these, you said, oh my God, let me start looking where it's concentrated. This is point of sale, because all God's children in retail want to know about point of sale. Who bought what? The employee system needs to know, loyalty program, price optimization, inventory needs to change. Point being, if you're a retail architect, you know all this stuff. And you're going to architect your application to fit in there seamlessly, right? But it's a different diagram for the other types of architects. So when you say, thinking like a software architect, we've been talking about thinking like all software architects. But if you're going to drill down and be a software architect for a company, or you want to be a software architect for Home Depot, you're going to be a software architect for Travelers Insurance, you're going to be all of these people. And most of the programs in the United States are working on, for companies like this, or for companies that sell to companies like this. One of the things you might do as an exercise is, and I should have it. I'd show it. Well, I could share the screen, but you could do it. Capterra, CAPTERRA. Go there and look up enterprise. No, look up enrollment systems at colleges, and you will find 33 vendors that sell that product. Companies you've never heard of. They're all out there, and they're all selling to colleges. And that's just one application in one domain. And when you think about all the ways that the world works, Um, it is it is sobering to realize how many companies there are that you've never heard of that are architected according to these rules or whatever rules they use, um, uh, to make the world work inside of corporations. Okay, so let me answer the questions that we had at the beginning. How and what to think before you code. That was everything we've talked about in this presentation. How thinking can be reused exactly like code can to design patterns. The driving force behind software language development, precise definition of architectural abstractions, that's structs, and encapsulating them, objects. And developing those was the evolution. Where it's going is English, but we're not there yet. How to construct a common application language, the importance of that, have it spoken by domain experts, end users, and programmers, so that when the domain expert says foreign students are the fees, the student fees on foreign students are going to go up or something, the programmer knows that, or the prereqs for this course have changed. The programmer understands that before a student can enroll in a section, they have to add that section. They're going to add the prereq so that all of that's going to seamlessly work because they're all talking the same language. Um, it is possible to debug a design. We didn't get into that nearly as much as I would have liked, but if you go through each of the use cases and you create a sequence flow, you will then have, for each object, you will have all of the public methods that need to be there to support all the use cases. And that, in a way, is you've debugged the design in terms of knowing that the objects that you have created, constructed, architected can support the requirements of all the use cases that you've got. Um, how to package and integrate an application in the corporate enterprise. We looked at three-tier models and the corporate enterprise DB. How to tie architecture into AI. The blueprints are, in a way, AI prompts, and there is now a way to give a description. There is a language, um, uh, which I should know, but I don't. Um, it's a language for generating. You have a lot of AI tools that don't generate the diagrams, but they generate this UML markup language that can generate the diagrams. And so we're getting to the point that if you describe things, you can get the UML artifact if you need, but you can supply the UML artifacts and they will in fact generate code. It's usually code that is missing stuff, but as you refine it, it's getting better and better, um, to the point that eventually, this is the future. The software architect programs in English, and the English is producing the diagrams that define the projects from which AI and Copilot and programmers can implement. I think they'll always be fitting stuff into an enterprise, but that's okay. We're now at a question point. Let me look at the folks have stayed with me. I really appreciate it. Let me look at the Q&A. Okay. Cost efficiency, um, choice of programming languages, and carbon emissions. Okay. I haven't spoken. I actually haven't thought about carbon emissions, so I can't really speak to that. Um, uh, Other than to say that, well, as of cost efficiency. So let's talk a little bit about that. Um, uh, Cost efficiency is there's two kinds of cost efficiency. Well, you think about what are the goals of when you're programming, you're trying to make it run as fast as it can and the limited space that it can to be robust and so on. When you're architecting, you're not so much worried about performance. That's a terrible thing to say, but I mean, in a sense that if it doesn't run fast enough, you know, you can wait 9 months and there'll be a new machine out there that will do it in the time. Anyway, it's not so much performance as it is robustness and extensibility because applications change and they increase their functionality. And what you're worried about is how much does that break? If you're trying to architect it so that things don't break, and you do that by encapsulating everything behind object walls and leaving as little knowledge of how the object does what it does, as little knowledge of that in the public methods. You say enroll a student in section, and it says got it. That's as much as you say, and all of the magic is being done behind that wall. So performance, which is all about horsepower and how many how much juice you suck up with your application, um, isn't something that I'm architecting for. I'm architecting for, encapsulation, loose coupling between modules, and so on. Um, the cost efficiency, though, there is a way to architect that because there are people who do this for a living. You're trying to put it into the cloud, but you're trying to do that in as efficient way as possible because the bills that you get from the cloud provider can vary greatly based upon how you figured out how to how to migrate your application to the cloud. Um, and there's another lecture there for sure, and maybe even a course that says here are the different cloud providers, here's typical applications, here's the things you put in the cloud, the things you keep behind, here's the best way to take your application and save a lot of money every month. And that would be cost efficiency. But you don't see that much at the architectural level. Long answer to a short question. Um, Let me look at the chat. Okay. Can you see specific domains as instantiations of a generic enterprise metamodel? Um, okay, I'm biased, right? I was uh, CTO of an individual. Well, my background was I was. So the question is, can you see specific domains as instantiations of a generic enterprise metamodel? And I can't. Um, uh, but I can see something like that. So to give you the background of it, I was working for Sun Microsystems as a Java evangelist, and that I wound up dealing with a lot of industry standards, hoping that to get them to adopt Java meant that we could evangelize developers we'd never have to meet because they were implementing the standard. And so I got to sit on a lot of different industry standards committees. And I realized that there were common things going on in all those standards committees, but they didn't know it. They were trying to work within the retail space or the educational space or, whatever. And, what I started realizing was that they were all trying to deal with data models and they were all trying to deal with, how to integrate an application into an existing environment. Um, they the model that I put up for retail, that horrible picture of all those, that's unique. I couldn't figure out a generic way to do that. The best that you could do is to come up with here are the tools that you use. Everybody's going to use SQL. Everybody might be using, so you could do that. And some of the it was hard. I mean, there are models, but they're not design patterns, they're architectural patterns. We don't have time to go into that, but an architectural pattern is as close as I can get to answering that question. An architectural pattern would be like request fulfillment. Um, uh, uh, Yeah, and resource provisioning and request fulfillment. And there are things you can say about those that transcend verticals because they're analysis patterns, they're architectural patterns, not design patterns. But that's another lecture. And you could only attend that lecture having heard this lecture. Because the things that go into making a design pattern are the basis of what goes into making an architectural pattern. But that transcends the specifics of the design. So yes, kind of. I can see it, but I can't explain it in less than an hour. So it's a great question though. Um, okay. I think that's the questions that, oh, will the presentation slides be available for download? Um, will Megamind make that available?
So what we have, it will be in YouTube channel. Our lecture will be edited. They can see the lecture again in YouTube channel.
If you see the lecture, okay,
Yeah.
fine.
Yep. So thank you, Ron, for the great
Sure.
presentation, and thank you everyone participating. Actually, it was a really good ending number for 2 hours lecture. I appreciate it. Very engaging. People enjoy. Thanks. Hope to see you in our future events. Let us know if you have any questions. You can send us an email. Thank you, Ron, again. You took really great
Sure.
time and prepare for it. Appreciate it.
All right, you take care. Thanks so much. Bye.